Rolling motion. When any object rolls, it performs translation motion and rotational motion simultaneously. Here, this football, bowling ball, wheels, wheels of car, billiards ball perform rolling motion, that is, they all perform translation motion as well as rotational motion simultaneously. Consider a purely rolling motion of a wheels of car. Here, wheels of car perform the translation motion as well as rotational motion. In this case, it is very difficult to describe the motion of individual particle of this wheel, and hence we can consider the actual motion to be the result of circular motion of a body as a whole about its own symmetric axis, which is passing through the center of the wheel, and the linear motion of a body assuming to be concentrated at its center of a mass. So in other words, we can say that the center of mass of the wheel performs the purely translation motion, and other particles of the wheel performs rotational motion about the axis passing through this center of mass. Here we can see the arrow which shows the translation motion, that is a straight motion of the center point of the wheel. Consider the rolling motion of this football. In a rolling motion, the object has two types of kinetic energies, and they are rotational kinetic energy and translation kinetic energy. The total kinetic energy of a rolling body is a sum of these two kinetic energies. To find out the total kinetic energy of a rolling body, we have to consider an object of a moment of inertia I, which is rolling uniformly, and we have to consider the following quantities, that is v is a linear speed of the center of mass of that object, r is a radius of the body, omega is a angular speed of a rotating object. In terms of linear speed, we can write the omega is equal to v upon r for any particle. Capital M is a mass of a body. K is a radius of gyration of a body. In terms of radius of gyration, we can write the moment of inertia of this rolling object is equal to mk square, and by definition we can write the total kinetic energy of a rolling object is equal to translation kinetic energy plus rotational kinetic energy. Substitute the value of each term in this equation. Total kinetic energy of a rolling object is E. Translation kinetic energy is half mv square. Rotational kinetic energy is half I omega square. Now substitute the value of I in terms of radius of gyration, that is mk square, and also write the value of omega in terms of linear speed v. So we can write the E value is equal to half mv square plus half mk square into v upon r the whole square. Open the bracket, and it is found that half mv square is a common factor, and we can take it out of the bracket, and we can write the equation as E is equal to half mv square into the bracket 1 plus k square upon r square. This is the total kinetic energy of a rolling object when it is rolled down from an inclined plane. So it must be remembered that the static friction is essential for purely rolling motion. In this case, it prevents the sliding motion. You might have noticed that many times while rolling down, the motion is initially purely rolling motion, and later on it turns to be a sliding motion. So it just gets slide on an inclined plane. Similarly, if you push a spear-like object along the horizontal surface, initially it slips for some distance and then it starts rolling, and thus without a static friction the object cannot be rolled. Either it will be rolled first and then slips down, or it will slip or slide first and then roll. Let us find out the expression for linear acceleration and linear speed while an object rolling down on an inclined plane surface. So that object can be a football, or the person is sliding on this slide, or any object is get lifted and is rolling down an inclined plane. Let us find the linear speed of an object while pure rolling motion down on an inclined plane. Consider the figure in which the rigid object of mass m and the radius r rolling down on an inclined plane without slipping. Here, theta is an angle between the inclined surface and the horizontal surface. As the objects start rolling down, its gravitational potential energy is converted into the kinetic energy of a rolling object. Starting from the rest position, let v be the speed of the center of the mass of the object as the object comes down through the vertical distance h, which is equal to s into sine theta. We know that total kinetic energy of a rolling object is a summation of translation kinetic energy and the rotational kinetic energy. Just substitute the value of each term. We can write E is equal to half mv square plus half I omega square. Just substitute the value of I in terms of radius of gyration, that is mk square, and omega is equal to the v upon r. Then it is found that half mv square is a common factor and we can take it out of the bracket, and we get the total kinetic energy of a rolling object is equal to half mv square into 1 plus k square upon r square. Here we know that the object is rolling through an inclined surface and it is always lifted up to a distance h. So when it is get lifted up to a distance h, it always governs some gravitational potential energy, that is GPE, and when it gets rolled, this gravitational potential energy is converted into its total kinetic energy. Hence we can write the equation as total kinetic energy of a rolling object is equal to that mgh, and we can write the equation as E is nothing but the total kinetic energy, that is half mv square into the bracket 1 plus k square upon r square, that is equal to the gravitational potential energy, and that is nothing but mgh. So once you get this equation, we can just rearrange the term. The two factor is moving from left hand side to the right hand side and it's get multiplied to the mgh, and also we can cancel out the common factor m from both the side, and we get the equation of a v, that is a v square, that is 2gh upon 1 plus k square upon r square. So this is a v square value. We want a value for the linear velocity of an object while rolling down on an inclined plane, and hence we take the square root of this factor and we get the value of the v is equal to square root of 2gh into 1 plus k square upon r square. So this is the expression for the linear speed while an object rolling down on an inclined plane, and the unit for the velocity is same, that is nothing but meter per second. We'll find out the expression for the linear acceleration of an object while performing a pure rolling down motion on an inclined plane. Consider a rigid object of mass m and the radius r is rolling down from an inclined plane from the height h. So the linear distance traveled along the plane is given by s is equal to h upon sine theta. During this distance, the linear velocity has increased from initial velocity 0 to the final velocity v. If a is a linear acceleration along the plane, we can use a kinematic equation, that is v square is equal to u square plus 2as, and rearrange the term. We can write the equation as 2as is equal to v square minus u square. Now substitute the value of s, that is h upon sine theta, in this equation. We can write 2a into h upon sine theta is equal to v square minus u square. We know that v is a linear speed of an object which is rolling down from an inclined plane, and that value is v is equal to square root of 2gh upon 1 plus k square upon r square. Hence we can write the v square is equal to 2gh upon 1 plus k square upon r square, where k is a radius of gyration and the initial speed value is 0. So we can write here u is equal to 0. Just substitute the value in this equation. We can write the above equation as 2a into h upon sine theta is equal to 2gh upon 1 plus k square upon r square minus 0. So this value also comes to be 2a into h upon sine theta is equal to 2gh upon 1 plus k square upon r square. Now just cancel out the common term, that is 2 factor from both the side. Also h is getting cancelled out from both the side, and we can write the equation as a into the bracket 1 plus sine theta is equal to g into 1 plus k square upon r square, and hence the a value can be written as g into sine theta upon 1 plus k square upon r square. So this is the expression of linear acceleration while an object rolling down on inclined plane. Let us know some factors about the rolling motion. For pure sliding without friction, the acceleration is g sine theta and final velocity is square root of 2gh. So we can substitute the value and we can find out the acceleration and the velocity of an object in a pure sliding motion. Thus, during the rolling motion, the factor 1 plus k square upon r square is effective for both the expressions. For rolling object, if the expression for a moment of inertia is of the form n into m r square, the numerical factor n gives the value of v square upon r square for that object. For example, for a uniform solid sphere, I is equal to 2 by 5 m r square is equal to mk square, and hence the mk square upon r square value gives the value of 2 by 5, and this way we can find out the k square upon r square is equal to 1 for a ring or a hollow sphere. And similarly, we can find out the value of k square upon r square for a different object, that is a symmetrical object. It is 1 for a ring or a hollow sphere. It is equal to half for a uniform disc or a solid cylinder. It is equal to 2 by 3 for a thin walled hollow sphere. When a rod rolls, it is actually a cylinder and that is rolling. While rolling, the ratio of translation kinetic energy to the rotational kinetic energy to the total kinetic energy can be written as 1 raised to k square upon r square raised to 1 plus k square upon r square. For example, for hollow sphere, the rotational kinetic energy can be given by k square upon r square, and that is equal to 2 by 3. Hence, we can find the ratio for the rolling motion in terms of translation kinetic energy to the rotational kinetic energy to the total kinetic energy as 1 raised to 2 by 3 raised to 1 plus 2 by 3. Just solve this bracket. It can be written as 5 by 3, and then cancel out the denominator term 3 from all the three sides. We can get the ratio as 3 raised to 2 raised to 5 for the rolling hollow sphere. Hence, we can say that the percentage wise 60% of its kinetic energy is a translational and the 40% energy is rotational.